You've probably had this happen. You ask an AI a pretty simple question, and it gives you back an answer that sounds completely plausible, but it's totally made up. This is called hallucination, and honestly, it's one of the biggest things holding back our trust in AI. Well, today we are doing a deep dive into a really fascinating paper that gets to the absolute root of why AIs do this. And the reason, well, it's way more fundamental than you might think. Let's get into it. So, to kick things off, get a load of this. The author of the paper, Adam Kalai, asked three of the top language models in the world a really simple question about himself. What was the title of your dissertation? And look at the results. GPT-4o, DeepSeek, and Llama all came back with completely different answers. They all sound believable, but they are all 100% wrong. I mean, they didn't just miss the title. They got the university and the year wrong, too. This isn't just some random error. It's a huge clue pointing to a much deeper problem. And that brings us to what a hallucination actually is, because the definition is key here. It's not just about being wrong. The paper defines it as a plausible, overconfident falsehood. The AI doesn't just make a mistake. It serves up that mistake with all the confidence of a certified genius. And that's what makes them so dangerous and so misleading. Okay, so to figure out where these confident falsehoods come from, the paper first looks at how these models are built in the first place. And here's the big reveal. Hallucinations aren't really a bug. They're actually a natural, almost predictable statistical outcome of the way we train them. Now, this is where the paper gets really clever. Instead of trying to solve the massive problem of generating perfect sentences, the authors simplify things way down. They ask, what if we just give the AI a much simpler job? Just a simple yes or no. Is this statement a valid fact? For instance, there are two Ds in ladder. Is that valid? Yes. There is one G in cat? Valid? No. This simple change in perspective is the key that unlocks the whole problem. So this simple yes-no task is really the foundation of their entire argument. Step one, they show that you can take any big language model and use it as this kind of simple fact checker. Step two, we've known for decades that these simple classifiers are never perfect. They always make some mistakes. But here's the real breakthrough. Step three, the paper provides mathematical proof that the mistakes made in this simple yes-no task are directly and unavoidably linked to the complex hallucinations we see in the model's generated text. And boom, this is it. This is the mathematical heart of the paper. The rate that a model hallucinates when it's generating text is fundamentally tied to, and at least twice as high as, its error rate on that super simple yes-no task. Think about what that means. If a model has even a little bit of trouble just recognizing a false statement, it is mathematically guaranteed to have an even bigger problem generating truthful statements. Hallucination isn't an accident, it's a predictable multiplier of a more basic flaw. So why do those basic classification errors even happen? Well, the paper points to two classic reasons from statistics. First, you've got a poor model fit. Imagine you have data points that form a circle, but you're only allowed to use a straight line to describe them. You're just going to be wrong a lot of the time. The second reason is when there's no real pattern to learn at all, like trying to predict a list of random birthdays. The model can't learn a rule, so it just has to memorize. And for any birthday it hasn't memorized, all it can do is guess. These are the tiny statistical seeds from which giant hallucinations grow. All right, so that explains the nature side of the problem, where hallucinations come from in the raw training data. But what about the nurture side? Why do these models keep hallucinating even after we've fine-tuned them to be more helpful? That brings us to the second major idea in this paper, what they call the test taker's dilemma. The paper gives us this perfect analogy. Think of a language model like a student who's taking a really important exam. The rules of the exam are simple. You get 1 point for correct answer, but for an incorrect answer, you get 0 points. And for leaving an answer blank, you also get 0 points. So if you're that student and you aren't sure about an answer, what's your best move? Let's just do the math. It makes it super obvious. Let's say you've got Model A, the honest student. It knows 8 answers for sure, but it's shaky on the last 2, so it leaves them blank. Final score? 8 out of 10. Pretty good. But then you've got Model B, the savvy guesser. It also knows the same 8 answers, but on those last 2, it just takes a shot in the dark. Even if it only gets one of those guesses right, its final score is now 9 out of 10. In this system, there's absolutely no downside to guessing, so it's always the best strategy. The system literally rewards guessing.
And this leads to a really stark observation in the paper. For you and me, exams are a temporary thing. We go out into the real world and learn that sometimes saying I don't know is actually a really valuable and respected response. But for AIs, it's totally different. They are constantly being judged on leaderboards and benchmarks that use this exact scoring system. So, in a very real sense, language models are always in test-taking mode. And hey, this isn't just a hypothetical. The researchers went out and analyzed the most popular, most influential benchmarks in AI, the very tests that decide which models get billions in funding. And look at this table: MMLU Pro, GPQA, SW Bench, it doesn't matter. The scoring is basically always correct or incorrect. Now look at that last column. Credit for I don't know? The answer is a resounding no, 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 all the way down. The entire ecosystem is built to reward the savvy guesser over the honest student.
Okay, so that's the diagnosis. Hallucinations are born from statistics, and then they're reinforced by the way we grade them. So what's the solution? Well, this is the really hopeful part of the paper. They argue that we don't need some magical new technology to fix this. We just need to fix the grading system. The fix they propose is what they call socio-technical, and that's why it's so brilliant. It means we don't have to re-engineer the AIs themselves, which is incredibly hard. We just have to change the rules of the game that all the AIs are being forced to play.
And here's what that change actually looks like. It's just a single sentence added to the instructions for the test. You tell the model, answer only if you're more than 90% confident. Why? Because a correct answer gets you 1 point. Saying I don't know gets you 0, but an incorrect answer now gets you a whopping -9 points. All of a sudden, the math is completely flipped. Guessing is now a terrible strategy. The incentive to just make stuff up completely vanishes.
So why is this one little change so powerful? Well, a few reasons. First, it makes the rules totally clear. The model knows exactly how confident it needs to be. Second, and this is the big one, it completely changes the model's motivation. The best way to get a high score is no longer to guess, but to be honest about what it doesn't know. And third, this isn't some far-off dream. We could apply this change to all the major AI benchmarks tomorrow. So ultimately, this paper leaves us with a really powerful thought. Maybe this whole AI hallucination problem isn't some impossibly complex technical glitch. Maybe it's a cultural problem, stemming from the tests we design and the behaviors we reward. And if we can start grading our AIs not just on how much they know, but on how well they understand the limits of their knowledge, we might finally start to develop AIs that learn the most human and maybe the most important skill of all, knowing when to say, I don't know.